Hey guys, welcome back. We are on day 9, integrated rate laws. We're going to do number 92. So the reaction of H2O2, hydrogen peroxide, going to water and oxygen gas is first order in hydrogen peroxide. And so, first order, we know hydrogen peroxide H2O2, and T1 half is natural log 2 over K. T1 half is natural log 2 over K. Got it. Under certain conditions has a rate constant of 0.00752 seconds at 20 degrees Celsius. Initially it gains 150 milliliters of 30% by mass. It gives you a density. Alright, guess. Alright. It gives you a density. It says the oxygen's collected over water at 20 degrees Celsius. It forms what volume of O2? There's your question. Forms in 85 seconds under a barometric pressure of 742.5 millimeters, and the vapor pressure of water at that temperature is 17.5 millimeters. So what is going on here? Okay, so imagine you have a container. And in this container, right, it's sealed, and it has a lid on it. Oh. And in here you have H2O2, and it's decomposing. All right, and if we can collect this tube, it can go into a container, right, where it's sealed. And there's water here, and this is sealed, right? The H2O2, the bubbles, O2, will go in and be up here, right? And we want to know how much O2 can we collect. That's one way to do it. There's other ways to do it. It looks very much like a barometer. All right, I can draw a barometer here. So imagine you had something like this, right, where you have H2O2 and the bubbles, the O2 is going up here, right, something like that. Either way, okay, how we want to set up the experiment, probably on the right's a little bit better than the left for this case, because you have, hydrogen peroxide is a liquid, and we want to make sure all the oxygen gas goes into the tube. Right, we want to know, we got to do a couple things here. So we have the hydrogen peroxide, H2O2 aqueous, going to 2H2O liquid, and O2 gas. I want to know the volume of this gas. All right. We know about H2O2 that I have 150.0 milliliters. It's 30%, and it's 1.11 grams per solution, per milliliter. All right. Well, let's break these down. All right, I like to do this. So the 30% is really 30 grams of H2O2 per 100 grams of solution, right? That's our mass percent. And the density, why is it doing that? Let's try that one more. There we go. The density is 1.11 grams of solution per 1 milliliter of solution. All right, those are our units. So that makes this a little bit easier. And that 150 milliliters is of solution, right? Okay, and that's the amount. It's also the amount. That's the amount, right? So the mass percent's a ratio, the density's a ratio. I can probably get how many moles of hydrogen peroxide. So let's try it. Let's try it. If I take 150 milliliters of solution, we know every 1 milliliter of solution is 1.11 grams of solution. And then we'll check up to know that for every 100 grams of solution, I have 30 grams of H2O2. And then we know that 1 mole of H2O2 is 34.02 grams of H2O2. All right, 16 is 32, plus the 2, 34. And then the O1s. All right, so if we take our 150 times 1.11, so 150 times 1.11 times 30, divide 34.02, I should get, I didn't divide by 100, right? Divide by 100 for the mass in the solution. There we go. 1.47 moles. 1.47 moles. H2O2. I want to point something out what I just did right there. I forgot to divide by this 100 in my calculator because, right? Well, I got 146 moles, 147 moles. That seems like an awful lot, doesn't it? So that's why red flag, that probably is not a good answer. All right, and so then looking at the work, yep, I forgot to divide by 100, right? That's a good habit to develop. All right, going back to this, my molarity, because again, up here, this is concentration, isn't it? So my molarity now, the molarity of H2O2, the moles, 1.47 moles, divided by 0.150 liters, right? Okay, and so this is where I get lazy. I just divide by, take that number of moles, divide by 0.1500. I get 9.79. Technically speaking, I should have done 1.47 divided by 0.15. And I get 9.8, which I could use 9.80 because I have 3 sig figs. All right. So does that make a huge difference? It's probably not going to make a huge difference. All right. But just so you know, that's where sig fig comes. Now, our current textbook says we round at the end. Okay. So I'm going to keep the 9.79 because I'm supposed to round at the very end of the series of calculations, not at the end of the problem, basically, not during the middle. Okay. All right, so now with this concentration, I can go into our first order rate law and figure out H2O2 at time t. So H2O2, what we're looking for, 9.79 molar there. All right, because this is time t, this is time 0. E, negative K. K was 0.00752 seconds negative 1. And T happens to be, what, 85 seconds? Is that right? Yeah, 85 seconds. All right, let's put this into the calculator. So I take my 9.79 times second log negative, we got 0.00752 times 85, and do I get 5.17? Perfect. And just to check, no, I'm going to do it this way. If we were to use 9.80, what do we get? 5.17. So it would have washed out right there anyway. So 5.17. All right, what is that? That is our remaining. All right, that's remaining. So one of the reasons I like this is that hydrogen peroxide, a lot of us have that at home. And when we have this at home, there's an expiration date on it. Now, some expiration dates are completely arbitrary. They're just on there. All right, milk's a good example of this. So there's milk that people have drunk that is a week past the expiration date and it's fine. And there's milk that you open up and it's before the date and you open it up and it's no good, right? But it's not even to its expiration date. And it has to do more with what bacteria and how the milk, that got into the milk and whatnot, and what happened inside the milk versus the date, right? Sometimes that date can be way off. The hydrogen peroxide, that does decompose sitting there in the bottle. It does. It's a small amount per time. So when you're after it's 3% to begin with at home, and as it decomposes, it gets less and less. All right. But yes, that's how hydrogen peroxide works. So that's why there's an expiration date. Sometimes expiration dates really mean something, and sometimes they're not. Like if you had table salt at home and there's an expiration date on it, that's kind of absurd. Sodium chloride's not going to decompose, right? But if you have, ranch dressing at home, it will go bad, right? So there are times where the expiration date is really warranted, so especially with medicines. So if you have medicines and they're expired, you might want to really take that in consideration in case there is breakdown of the chemical compound. All right, going back to this. All right, we have that much remaining. We know we had to start with. We want to know how much reacts, right? Because we want to know ultimately how much oxygen is produced. So if I need to know how much oxygen is produced, I need to know how much hydrogen peroxide reacted. Well, if I start with 9.79 molar and I end with 5.17 molar, that would suggest that 4.62 molar H2O2 reacts, wouldn't it? Right, so if I take my 150 milliliters, and we know that for every 1,000 milliliters, I have 4.62 moles of H2O2, right? So 0.15 times 4.62, that would be what, 0.693? 0.693 moles of H2O2 reacts. All right, now we're going back to the stoichiometry. I have 0.692 moles of hydrogen peroxide. How much oxygen do I get? And actually, I didn't write this right because there's a 2 here. Almost messed up big time, right? So it's 2 to 1. So this is Chem 1 right here. I would take my 0.693 moles of H2O2. I would do 2 moles of H2O2, 1 mole of O2. And that gives me what? Divide that by 2 is 0.347, I believe. .346, yeah, 347. Perfect. So that's how much moles of O2 we have. Now, we're collecting a gas over water, right? So the volume formed is at that pressure, but we have water at this pressure, right? And so if you remember some gas laws, we're going to have to subtract the water because there's water up here too. And just like total mass, right? Like if I go to get on a scale right now, I got shirt, pants, belt, shoes, socks, watch, ring, wallet, all on me, right? And a headset too on top of that for this video's purpose, right? So all that contributes to the mass of the scale. Now, the shoes, the clothing, right? My watch and my ring, my wallet, that all has mass, and that's not me, right? And so like this is big in the doctor's office. A lot of people go to the doctor's office, especially if it's cold outside, and they have a lot of clothes on, and they just get on the scale, and there could be more than 5 pounds of material on you, and they just weigh you, right? And that happens. Okay, and so, right, back to pressure. The pressure just measures the total pressure. It doesn't measure the individual pressures of oxygen, right? And so we know the vapor pressure of water because it's totally temperature dependent, right? We know the vapor pressure of water, so we can subtract the water from the total and get oxygen. And so that's what we're going to do. So the pressure of O2 equals the pressure total minus the pressure of H2O vapor. So the pressure of O2 is equal to that total pressure of 742.5 millimeters of mercury minus the 17.5 millimeters of mercury to give us, what is that, 742.5 minus 17.5. So that would be what, 725? Now, we're going to put this in the ideal gas law. Can't use millimeters of mercury. We know that 1 atmosphere is 760 millimeters of Hg. So divide that by 760. And I get the pressure of O2 here to be 0.954 atmospheres. So we're going to throw this into PV equals nRT, correct? P, we got P, 0.954 atmospheres. I'm looking for the volume. N is, we just calculated, 0.347 moles of O2. R, of course, is R, 0.08. That's almost looking at a 1. 0.08206 liters, atmospheres, moles, Kelvin. And the temperature, go back up to the problem. What's that temperature? 20 degrees Celsius. Can we use 20 degrees Celsius? Of course not. So what is that temperature? Well, 273 plus 20 is, right, 293. So you can either, however you want to do that, you can leave it, I would either leave it as, in the parentheses, 273 plus 20, or 293. If you want to use 293.15, you can, or 293.2, you can, because technically you could do that. Alright, it's not going to change anything. Alright, so in our calculator, 0.347 moles times 0.08206 times 293 divided by, what was it, 0.954? I get 8.75 liters. Let's recap this. Shall we? Yes, we shall. Alright, so we have hydrogen peroxide decomposing to give us oxygen gas and water. We care about the oxygen gas, which does kind of make sense, right? Because if you're going to have something decomposed, do you have enough volume in your container to hold that gas. Otherwise, that container could explode, and that would not be ideal. So we found the amount of hydrogen peroxide in our 30% solution, which please don't buy. Right, that would start to dissolve humans. Right, 3%. That's 10 times more concentrated than what you guys have at home. So don't do that. All right, we can actually get it here. So water, or hydrogen peroxide, 150 milliliters. Did the density, did the mass percent, molar mass, got the moles, went back moles per volume, got the molarity. Did the first order kinetics to figure out how much is remaining at the end. Subtracted the start from the end to get how much reacted. And once we got the molarity, we used the volume and molarity to get moles. So we found how many moles of H2O2 reacted. Once we knew the moles of H2O2 that reacted, we figured out how much product of oxygen we made. Then we had to subtract the water vapor from the total pressure to get the pressure of oxygen gas. And we threw it into the ideal gas law, PV equals nRT. Had to make sure we changed our temperature to Kelvin, our pressure to atmospheres, solve for the volume, and that's the volume of O2. That's a pretty good problem. All right, if you have questions, let me know. Otherwise, take care.